So let's continue our lighting journey. Last time we implemented the irradiance from a configurable point light source and a kind of pass-through reflectance distribution function. But before we work some more on reflection, let's address the to-dos that I've made last time. The first one is here in common Odin about extracting the game state. And I made it because I found it annoying having to go to the command file to add game-specific things, and generally it feels kind of out of place. So let's go into our game Odin file and introduce the game state structure here. Now let's move our game-specific fields here, the pipeline and the sampler, the camera stuff, and all the others, the clear color, the rotation, all our entities, and the light configuration. And I don't want to do much more thinking and refactoring right now, so let's just add the game state field to our globals. And let's even add the using keyword before it, so we can still access its field using the same G accessor. This way we don't have to change more code right now, but we have the benefit that the game state is defined in our game file together with the other game-specific things, and we don't have to jump between files. Next we have this UBO separation to do in our vertex shader. And as discussed in the previous video, the view projection matrix stays the same for all the objects that we are rendering. So it's kind of global, and it would be nice to only push it once per frame, like we already do for our fragment shader uniforms. So let's split our C buffer into two, global and local. And note that they have different register bindings, so B0 for global and B1 for local. That's how we also differentiate between them on the Odin and the SDL side. Now let's go into our game Odin file and split our UBO into two as well. I named them using the same scheme as I used for the fragment UBO. And let's also add the packed directive, because even though the data layout matches so far, we should treat these structures the same way as our UBO frag global. Finally, let's go into our game render procedure and remove the old UBO pushing code and introduce a new one for pushing the local one for the entity containing only the model matrix, and push it to the slot 1, since this is where the shader expects it, right? And by the way, since we are drawing all our objects with the same pipeline, we don't need to bind it every time, so we can move this out of the loop. Now let's go to the beginning of the procedure, and next to our fragment globals pushing, let's push our vertex global to the slot 0. Just like this. Check if that still works. Yes, it does. So let's check the next to do. The next one is again in the vertex shader, and this is this one about the normal matrix for the normal transformation. Remember, I mentioned this article, and in this example here on the left we see the original shape and its normals, right? And if we apply a non-uniform scale, so for example only scale along the y-axis, we'll get the shape that is shown on the next pictures, right? And the center picture shows the normals if we simply transform them using the model matrix like we do currently. And while this is mathematically correct, this doesn't really make sense geometrically. And the third picture here on the right shows the correct normals for such a squashed shape. So how do we get them? Well, it turns out we just want to invert the scales while keeping the rotation. So basically, if the position was shrink by half along the x-axis, for example, then its normals should be doubled along the same axis. And we can do that with a special matrix called normal matrix. And you can read through that page for a deeper math explanation, but in essence, it's just an inverse transpose of the model matrix. Now this matrix is the same for all the vertices in the model, so let's just pass it in our local uniform buffer. And maybe we should have some clearer naming here instead of this single letter abbreviation, so let's rename the matrices while we're at it. Now let's change our normal multiplication to use the normal matrix. Remove this to do. Now let's go to our UBO structures on the Odin side and apply the similar renaming, and add the normal matrix to the local UBO. Now adapt our game render code for the new names. And now we need to calculate the normal matrix for the entity. And as I said, it's just an inverse transpose of the model matrix, and there's a handy function in the linalg to calculate exactly that. just like this. Now add this to the structure, run the game, and seems to still work. That's nice. Now there's one more to do left about making the attenuation more configurable, but let's keep it for now and come back to it later when we have different lights and better structure to represent them. And instead, let's finally work on our reflection distribution. So currently we have a constant value of 1 in all channels for our BRDF, which is then multiplied with the irradiance to get the reflection value. So we can think of BRDF value as a percentage of irradiance, so incoming light, that is actually being reflected off the surface. So the term reflection distribution makes sense too, right? And as I said, we'll be implementing the Blinn-Phong BRDF, so let's write a function like Blinn-Phong BRDF. And since it's a bidirectional function, it works with two directions, right? The direction to the light and the direction to the view. So let's add those directions as arguments. So let's make it work as before, so return 1 on all channels. And call this function from our main function. Now we already have our direction to light, since we use that to calculate the irradiance. We just need the direction to view. And we can of course calculate it exactly the same way as we do for direction to the light, but instead of the light position we use the view position. And we can use normalize directly, since here we don't need the distance, right? Now this view position is just a camera position in the world space. So this would be something that we just pass in our global buffer, along with the light information, so let's just add another field here. Now we add the view position to our fragment global structure on the Odin side. And we don't need any paddings here, as the field would already start at the next 16-byte row. And finally, we simply push our camera position as the value for this field in our frag global structure. Now we have everything we need to implement the Blinn-Phong BRDF. So this model defines reflection as two main components. Well, it's actually three, but let's talk about this a little bit later. And the first one is the diffuse reflection. It represents light entering the surface of the material, scattering around, and then exiting it in random directions, so virtually all the direction. And in addition, depending on the material, light of specific wavelengths may be absorbed. And in practice what this means is that this kind of reflection would be the same no matter which angle you look from. And the material can define what kind of light is reflected and what is absorbed. So let's type that out. And let's define that our material only reflects half of the red color and completely absorbs green and blue. So basically it reflects 0.5 of the red and none of green and blue. And let's directly return that from our BRDF function. Note that we don't even use any of the directions so far, because the diffuse reflection is assumed to just reflect light coming from anywhere in virtually all the directions, minus the absorbed part of course. See, the objects are now red, even though the light color is white, because all the other components are absorbed by the surface material, which results in zero multipliers for green and blue of course. And of course, if we change our diffuse reflection to only reflect green, our objects will appear green, right? So I think it's clear that the diffuse reflection, along with the incoming light, are the main contributors to the perceived object color. Now remember we have this color map texture for our objects, right? And well, what if we use it to sample the diffuse reflection values, basically giving it a new meaning within our shader? So basically if we sample red from it, our fragment will reflect red and absorb everything else, and thus define the perceived color of the fragment as red. Sounds good, so let's rename our text to diffuse map or something, because that's what it is now. And let's use that instead of hard-coding the diffuse reflection. Let's pass the UV coordinates as well, so we can sample the diffuse map, although we might want to just pass the sampled value later. And finally, let's use the RGB part of the sampled value, since we are not using alpha in any way for now. And this is starting to look pretty good, right? We now have our proper object colors back, but now they have a physical meaning and interact properly with lighting. So that's nice. Alright, the next component of the Blinn-Phong reflection model is specular reflection. And the specular reflection represents a light that didn't really enter the surface and thus was not diffused by it. And instead it was reflected directly off the surface. And we can basically only see it if the reflected light ray actually goes into our eye, right? So our task here is basically to calculate whether the radiance coming from the light source gets reflected into our view or not. Well, actually it's more like how much of it was reflected off the fragment surface directly into our view, based on the special shininess parameter that we can change for different materials. And this parameter basically represents how shiny or rough the fragment's material is. And it does that basically by introducing a very simple microfacet model, meaning that our fragment consists of many imaginary microsurfaces, and each of them is a perfect mirror. So the more shiny the material is, the less deviation of the orientations of those microfacets there is compared to the fragment's general orientation. And thus the less likely the light actually ends up going into our view, because the more perfectly the view direction must match the reflected light direction, right? And conversely, the less shiny it is, the more random the reflected direction is, and the more likely it hits our eye. So what did Blinn-Phong come up with? Well, while I can't say that I fully understand how exactly it was derived, it's still pretty simple to implement and get a general feeling for. So first we calculate this halfway direction vector between the light and the view direction. And this is just a normalized sum of direction vectors, so let's just type that out. Next, we use the angle between this halfway vector and the surface normal, or rather its cosine, and we get the value that represents more or less how close the reflected light is to the view direction. And if the angle is 0, so the cosine would be 1, the light is reflected directly, perfectly into the viewer's eye. So we are talking again about the cosine of the unit vectors, which is conveniently just a dot product, like this. Let's not forget to pass the surface normal as an argument. And also let's make sure that the value is never less than 0 using the max function. Because the dot value less than 0 would mean that either the light or the view is coming from the other side, which doesn't make any sense in this context. And finally we can calculate the specular factor using this value taken to the power of some shininess parameter. Let's hardcode the shininess parameter for now. Set it to something like 100. So this shininess number would give us this graph here. Basically the x here is the cosine between the reflection angle and the view angle, and the y is the factor, right? So basically the factor only starts to grow when the cosine is kind of closer to 1, right? We only start seeing the specular highlights when we are kind of looking directly at the light reflection. Now, if we would use a lower shininess value, something like 16 for example, right, the required angle would be much wider, so we would start seeing specular highlights much earlier. And if we change it to something even lower than that, then we would start seeing the directly reflected light from a lot of angles, which basically would mean that the surface is pretty rough. So the shininess would be a property of material, which means that we should move it into a uniform and pass through the game code. But for now, let's construct the specular reflection component. So for each channel we use just 1, and then we multiply it by the calculated specular factor, right? And then we just add the specular reflection to our diffuse reflection and return the BRDF value. Now we can run the game. and see how shiny everything became. Now we can stop the rotation and move around and see that the reflected light actually depends on the angle at which we are viewing. Now if we move the light, of course, that also affects the specular highlights. Now let's take a look at this float 3111 here that we use and multiply with the specular factor. This value actually also depends on the material. Normally the non-metal materials, also called dielectric, they reflect the light directly and do not change it, so they do not kind of absorb this kind of light. However, some metals, like for example gold or copper, they might absorb some of this light and never reflect it back, which would basically change the color of those specular reflections. So this is actually another property of the material. And actually, if we take a look at how we sample the diffuse reflection from the texture, we could actually do the same for the specular reflection setting and the shininess as well. However, of course, our current models do not have the specular map, so let's actually just move them into a local constant buffer, and maybe let's just configure it per object. So we define another C buffer at the register B1 and define the material specular color and the shininess there, and use them instead of the hard-coded values. Now go to the game Odin, of course, and introduce the UBO frag local structure. Add the fields here, and actually in our model, instead of texture, let's make it have a material instead, which would contain the diffuse texture, the specular color, and the specular shininess parameter. Now we can basically specify different materials for different models. So all our objects use the same diffuse texture, however they use different specular settings. For example, the tractor has no specular color and the shininess of 1, because that would be the minimum value for the power, right? But if we want to disable all the speculars, we would just pass the color as 0. So it would all be multiplied by zeros. Then the sedan has a proper full color specular reflection with kind of high shininess value. And the ambulance has this weird red specular reflections with a slightly lower shininess. Now, just to move around better, let's enable flying by commenting out this zeroing out of the Y movement coordinate. And finally, let's push the fragment locals here for each entity. So first we get the material from the model, construct the local structure, and push it to the slot 1. Then we of course change the texture binding to actually use the diffuse texture from the material. And now we can fly around and see that the sedan is pretty shiny, while the tractor is not shiny at all, it only has the diffuse reflection. And the ambulance has this weird reddish specular reflection, as if it's made of some weird metal. So yeah, as we can see, now we have the notion of materials, so it's kind of taking some shape. And of course, for like actual models, you would use a texture instead of one values to specify the specular and even the shininess, because you would like different parts of your model shine differently, right? And one more thing is that currently this emitted radiance is something that we just zero out and never really set to anything. And we could have yet another texture that would contain an emission color, and I think that's called emission textures. And this could be used for emissive parts of your model, like for example headlights on the car or something like that. Now what we could also quickly do is make the shininess parameters editable in the inspector. So let me do that. So something like this, for every entity we create a new separator text and create a color widget for the specular color and the normal drag float for shininess. One nuance here is that we need to do this push ID call to make ImGUI differentiate between different instances of these widgets. Otherwise it would just complain. So now we can play around with this. For example, this is our sedan. We can make it a bit more matte, right? Less shiny. So the speculars are kind of more distributed around the whole surface. Or we could make it more shiny to make it look smoother, right? We can do similar stuff with our other objects, right? Like this. We could change the specular highlight color and stuff like this, right? So this is of course possible. Now, if you remember, there's actually another component to the Phong model that tries to approximate a kind of random light scattered around from various sources, including the light being reflected back and forth between all the microsurfaces of all the objects, and the kind of general environmental light. And this is called ambient light. And there are different ways to configure it. You could have it as a property of each light or a global one. And then for each material you could specify how exactly it reflects that light. That all depends on how detailed you want it to be tuned. But for this video I'm just gonna introduce a separate positionless ambient light with a very low value, and then simply multiply the material's diffuse reflection value from the diffuse map by it, and just add it to the final reflection radiance. So let's add another field to the globals, something like ambient light color. Then actually move the diffuse texture sampling outside of the BRDF, so we can use it for both point light and ambient light. Maybe for the naming consistency's sake, introduce the ambient irradiance variable, that is just ambient light color. Set the starting value of the reflected radiance to the ambient irradiance multiplied by the material diffuse reflection. And make the other lighting calculation added to that value instead of setting a new one. And we can remove the else branch here. Let's add it to the fragment global UBO structure. Add it to the game state, to the inspector, also to the initial values, something very weak like this. Maybe it could be different if it's night or day, so the night would be more bluish and day would be more white or yellowish. Then we add it to the global UBO push in the render function. And let's not forget the padding here, because of course after the vec3 we have 4 bytes to pad. Now we can check how it works. Now you see everything is much brighter. Maybe the ambient color is actually still too bright, but yeah. Let's maybe tune that down, maybe to 0.01 or something like this. Now, even if we turn off the light completely, we can still see the shapes because of this ambient light, right? And we can change the ambient color, of course, as well. So now that's pretty much a full model of Blinn-Phong lighting. And maybe we should add one to do here, is that this BRDF is actually not a proper BRDF, because the proper BRDF is supposed to be energy conserving, which means that the amount of outgoing radiance should never be larger than the amount of incoming radiance. And with these calculations, it actually might happen that the diffuse reflection plus specular reflection has values more than the actual irradiance, which is not really physically accurate. So this is still something to research. Let's add a to-do here. So yeah, you see now our shader is of course much more complex or even complicated, and of course you can simplify the code here to make it more concise and simpler code-wise. However, I wanted to really illustrate the concepts here, so I have all this weird variable names and whatnot. So this could be also used for further exploration of physically based rendering and other kinds of BRDFs. So hopefully that was useful and not too confusing, of course. Yeah, I think next time we'll take a break from lighting and probably do something else, but also hopefully interesting. So stay tuned.